Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by clicking on the chat icon located in the lower right-hand corner of your WebEx window. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, John. Today's speaker is Dr. Jim Hughes. Dr. Hughes is a professor of biostatistics at the University of Washington and affiliate professor at the Fred Hutchinson Cancer Research Center in the Vaccine and Infectious Disease Division. Dr. Hughes works primarily in the area of HIV/AIDS research and sexually transmitted infections. He's been the lead statistician on a number of clinical trials in the HIV Prevention Trials Network, as well as other individually and cluster randomized trials in HIV and STI prevention. In 2007, along with Mike Hussey, Dr. Hughes published a groundbreaking paper outlining statistical approaches to the design and analysis of step wedge trials. And he continues to work on methods for step wedge trials to the present. It's my very great pleasure to welcome Dr. Hughes.
Thanks very much, David, for that kind introduction. Just want to acknowledge the collaborators that I've been working with presenting these results today. Students Emily Vodel and Avi Kenny. Fan Shah is a postdoc at University of Washington, and Patrick Haggerty, fellow faculty member there. So really broad outline, just a really short background on step wedge trials. I suspect that most of you are familiar with those. I know there's been a couple talks in this series on step wedge trials. But then focus on the first part of the talk on, what can go wrong in doing analyses of step wedge trials and some solutions, and then talk about some of the current research that we're pursuing in this area. So step wedge trial is a randomized trial, typically a cluster randomized trial. But unlike a classic cluster randomized trial where one group of clusters gets randomized to the intervention and one to the control, in a step wedge trial, instead you randomize clusters as to when they get the intervention. So in this little cartoon here that I've got, all the clusters start in the control condition designated by a 0 in this design here. And then one cluster is randomly selected to start the intervention, shown by a 1. And once the intervention is started, it continues. And then another cluster starts the intervention and another, and so forth over time. Conventionally, I'll use the notation that there are capital N clusters, so capital N is 3 here, and capital T time periods, 4 time periods here. The interest in most step wedge trials is in estimating the intervention effect. I put that in quotes for reasons that will become obvious as I go along, but you can see that there's an immediate problem or challenge with doing that, in the sense that by design, the intervention effect is potentially confounded with any underlying time trend. So if you did a simple naive comparison of the 1s to outcomes measured in the ones to outcomes measured in the zeros without accounting for any underlying time trend, then that could clearly produce a biased estimate of the intervention effect. So any analysis of a stepped wedge trial has to account for the potential for underlying time trends in some fashion. And a very common approach to analyzing stepped wedge trials is using mixed effects models. And so I've sort of outlined the backbone of a mixed effects model here where I'm measuring an outcome, Y, on individual K in cluster I at time J. And I assume that that can be written as a function of some underlying unspecified at this point time trend, which I'll beta of Ti, the time in cluster I period J. And a intervention effect. In this notation, the X, Ij, tells us whether or not we're in the intervention condition in cluster I at time J. So that's the zeros and ones in the previous slide. And delta is then the estimated intervention effect, or the parameter for the intervention effect. Importantly, the way I've written this, that intervention effect is assumed to be immediate. In other words, you get the full intervention effect once you go from control condition to intervention condition, and constant over time. So immediate and constant intervention effect. In addition to these fixed effects for time and intervention, one usually includes some collection of random effects to account for the correlation of repeated observations within a cluster. And so there's almost always a random cluster effect. There may be what's referred to commonly as a random time effect. Basically, the combination of these two allow you to have a different correlation for measurements within the same cluster time period versus measurements within the same cluster but different time periods. And then there may also be a random treatment effect. In other words, the effect of the intervention may be different from cluster to cluster, so we potentially allow for that. And there may be additional structure as well, and you may only want to be fitting a subset of these. So clearly, this is a very highly model dependent approach to analysis. So it seems reasonable to ask, what could possibly go wrong? And so I want to focus on a few different things here. I think you could think of more potential problems in this, but I want to focus on these particular assumptions. First one, maybe the easiest to discuss, is what should you do about that model for time? What if you get that wrong? For instance, suppose that you assume that the underlying outcome has an underlying linearly increasing time trend, but in fact it's not linear, it's some other shape. So if you chose the wrong model for time, then because of this confounding between time and treatment, you could bias the estimate of the treatment effect. Fortunately, this is probably the easiest issue to address in the sense that most of the time we're not really interested in the time trend, so we simply fit a very flexible model for time. For instance, in a stepped wedge trial with 4 time periods, we might fit a categorical model for the time trend with 3 dummy variables, or in general, T-1 dummy variables. And that allows for a flexible modeling of time. But we still are making an assumption is in that that underlying time trend is the same across all clusters. Potentially, though, you could relax that if there are obvious strata in the data. So, for instance, your trial is being conducted in 2 countries. You could allow the underlying time trend to be different for the 2 strata. So I think there are good solutions to that. And for that reason, I'm not going to spend a lot of time on this issue. The second issue I want to highlight is the possibility that you get the variance structure wrong. One challenge when fitting step wedge trials, especially if you put all these random effects in, is they often may not all, or the model may not converge when you have all those random effects in. And so you might be forced to, eliminate some. So one question that we asked was, does it really matter which random effects you choose? And particularly, we were focusing on the so-called random time effect and the random treatment effect. There was just some sort of vague thought when we started this work that possibly it doesn't matter because after all, time and treatment are a little bit collinear in the model, so maybe that somehow carries over to the random effects and it doesn't matter which one you put in. So Emily Votel, one of the students I mentioned at the beginning, has worked on this, now has a paper in Statistics in Medicine, where she basically looked at this issue of what happens if you include a random time, but you should have included random treatment or vice versa. The issue that arises is that you get wrong standard errors for the estimated treatment effect, unfortunately. And so let me basically show you some of the work that she did. She considered two cases because we were focusing on random time and random treatment and hoping maybe it didn't matter which one you chose. She looked at case one where the model, the true generating model, has a random treatment effect, but you fit a model with the random time effect. Case two is the reverse. True model is the random time effect, fit the random treatment effect. First thing we found, and this is actually well-known property of linear mixed models anyway, but that the fixed effects, in particular the estimated treatment effect, is unbiased, but the variance is wrong. In other words, the standard error of your treatment effect is wrong. And so to quantify how wrong, we created a quantity called the validity, which we called validity, which is the ratio of the model-based variance from the misspecified model. In other words, this is what you would see on your computer output if you fit the wrong model. This is basically what it tells you is the variance of delta hat when you actually fit the wrong model. And we divided that by the true variance of delta hat based on the misspecified model. Emily was a real tour de force, able to derive analytic expressions for these quantities, and so was able to easily and quickly look at how validity varies as a number of factors. And so maybe we hoped validity would be near 1, or at least that would be clear that it was always better to fit a random time effect or always better to fit a random treatment effect, but no simple messages. Basically, this is just one of the plots from Emily's paper. So color corresponds to validity, a value, a blue value, validity greater than 1. Let me go back to that picture here. So value greater than 1 means that the model-based variance you get from your computer output is bigger than the true variance. So you could say then that your confidence intervals are too wide, your inferences are conservative, maybe arguably a better place to be in than the other possibility where your model-based variance is too small. It's not capturing the true variability of delta hat, sort of akin to trying to analyze a cluster randomized trial and assuming all the data are independent, and you're going to fool yourself thinking your estimates are more precise than they really are. So this is basically what we found. So case one, recall, was when the true generating model had a random treatment effect, but we fit a random time effect. And if you only have 2 sequences, then that actually fitting the random time effect is conservative. So maybe you could argue in that case with only two sequences, it's better to fit the random time effect no matter what. If the true model has a random time effect, then you're good. And if it's truly random treatment, you're at least conservative. But unfortunately, that pattern only held for two sequences. Sorry, I'm not sure if I made it clear, but sequences are the number of patterns or the number of distinct rows in that stepped wedge design. So in the very first cartoon on the first page, we had three sequences. And in other cases, the fitting the wrong model was basically always anti-conservative, so validity less than one. And the degree of validity being less than one depends on a number of factors. It depends on the number of observations per cluster per time period, as shown here. They're getting redder as we go up here. And not shown here, but in other figures in Emily's manuscript, the validity also depends on the relative magnitude of the variance components. So unfortunately, there is no simple solution in most cases, except in the special case with two sequences where you could say it's better to fit a random time effect. I think basically what we concluded is first, it's better to overfit than to underfit the variance components. You actually don't pay any meaningful penalty by overfitting variance components, but you can pay a penalty by underfitting them. And then also, when possible, use a robust or sandwich type estimate, even on top of your mixed model. The issue there, though, is that often stepped wedge trials are conducted with limited numbers of clusters, and sandwich or robust variance estimators don't perform very well when the number of independent units, the number of clusters is small. So there's still work to be done, I think, there. Last thing I want to talk about, recent work that Avi Kenny, student, has been leading, is this issue of what happens when the treatment effect is not constant. So incorporated in this classic step wedge model is this implicit assumption that once the x turns from 0 to 1, once the treatment is applied, you get the full treatment effect instantaneously, and it's then constant as long as the treatment, as long as the cluster is observed. So we ask the question of what happens if you assume the treatment effect is immediate and constant. We call that the IT, or immediate treatment effect model, but it's really not. And we looked at a number of different scenarios. Let's start in the leftmost panel here. In each of these panels, I should say, the x-axis is the exposure time. So how many time periods has it been since the intervention was introduced? 0 represents the control condition. 1 time period since the intervention was introduced, 2, 3, so forth. And the y-axis is the treatment effect, arbitrarily scaled to a maximum of 1. The blue line represents the true treatment effect curve, or treatment effect exposure response. In the leftmost panel, we see that this is basically the case that most step wedge analyses implicitly assume, that the treatment effect is immediate once applied and then constant over time. We see that if that's the case and we apply that model that makes that assumption, then the model unbiasedly estimates that treatment effect. So far, so good, exactly what we'd expect. But what happens in some of these other cases where that assumption is violated? If we look at panel B here, in this case, the true effect curve, basically there's no effect. There's a lag in the effect for a couple time units. And then we see a rapid increase in the effect. We get to the full effect by time unit 3 and so on. Now, one would hope that the immediate treatment effect model, while admittedly violated, might, I don't know how to say, fail gracefully, in the sense that you might hope that it would give you some sort of average treatment effect, you know, an average of zeros and an average of ones, so it might be somewhere in here. But in fact, that's not what happens. what actually the estimate you get when you assume the treatment effect is immediate and constant is a small treatment effect in the opposite direction of the actual treatment effect here. So this is actually a negative estimate of the treatment effect, even though it starts at 0 and then goes up to a +1. So extremely counterintuitive result in this case. Looking at panel C, well, at first glance, this looks a little better here. We have this sort of curved treatment effect, and the estimated treatment effect is some sort of average over these points. But as you stare at it for a while, you kind of begin to think it's not a great average. I mean, 5 of these 6 post-exposure points are above the average, and only 1 here is below it. So it seems maybe a bit lower than I would have expected intuitively, perhaps. And then in panel D, we see, again, back to this very counterintuitive result where we clearly have an increasing treatment effect that achieves its maximum after a few time periods, but the estimated treatment effect from the classic IT model is essentially 0. So I will say, when we first saw these results, we were really surprised, I guess, to say the least. You know, if we want to get into it in question and answer, I have a little bit of intuition as to why it happens, but really what I want to focus on here is then, okay, what should we be doing about it? What should we be thinking about especially if we're concerned that we have a stepwise trial where the treatment effect may not be immediate? And so the first thing I think you have to think about very carefully then is exactly what you mean by the treatment effect, if the treatment effect is not this immediate constant sort of thing. Because now there's no unique definition of the treatment effect. You could say that perhaps you're trying to estimate the treatment effect at a particular, say, 2 or 3 time units after the start of the intervention. Or maybe you want to average the treatment effect over an interval. Or perhaps you want to estimate the treatment effect after some predefined phase-in period. Or possibly you just want to estimate the whole treatment effect curve. So I think it's really important then to think about in these situations how you want to define the treatment effect. And that's got to be driven by the science. But then given that you have come up with a reasonable estimand, then the question is how should we fit that estimand? And what we've basically come down to is essentially trying to do it not by modeling assumptions, but rather trying to keep a very flexible form for the treatment effect curve and then estimate the appropriate quantity sort of after the fact. So what do I mean by that? What we propose is altering the classic stepped wedge model to include what we call an exposure time indicator. In other words, now we're going to let delta, instead of be a single number, be a function of exposure time. So there'll be a delta sub 1. What is the treatment effect after 1 exposure period? Delta sub 2, what is the treatment effect after 2 periods, sub 3, and so forth. So you estimate all of those deltas individually, allowing the form of the treatment effect curve to be very flexible, and then you form an estimator based on those delta for whatever you're trying to estimate. Here I've basically expressed my estimate as an average of those deltas over some particular set of time periods. So this has the advantage that, like, suppose that you have decided, well, I think I should allow for a 2 time unit phase-in period. You could build that into a model where you would allow, say, delta 1, delta 2, and then a single delta after that. So that would be imposing the immediate or constant treatment effect assumption after 2 time periods. But our concern there is that if you're wrong, then you could get into these same counterintuitive sort of estimates. So keeping it totally flexible like this then allows us to form an estimate that will fail gracefully. So if I average everything from period 3 through the end of follow-up, but it isn't constant over that time period, I'll still get a reasonable average using this approach. So this gains robustness in that sense, but it unquestionably sacrifices efficiency compared to what you would get in terms of a standard error when the model assumptions are true. And I'll show you at the end a little simulation that kind of quantifies that. Okay, so basically then recommendations from this section is first off, always fit a flexible time effect, could be categorical time if time is a discrete variable, or some sort of flexible spline if you have many time intervals or somehow dealing in continuous time. It's generally better to overfit than underfit random effects. And if there are sufficient clusters, then even with a linear mixed model, use a robust or sandwich type estimate, but with the caveat that approach does not work very well when there are small numbers of clusters. And Jennifer Thompson has a nice paper on this. And then basically from this last bit, the stuff that Avi's been working on, that's under review in statistics and medicine, basically avoid fitting the IT model unless you're very confident that the treatment effect is indeed immediate and constant. Even though it sacrifices efficiency, it's certainly safer to fit a model based on this exposure time indicator sort of approach. Okay, so that wraps up that section. Now I want to spend the rest of my time basically talking about current research directions. And this is work that's been led principally by Fan Shah, who is a postdoc at Washington and former student there. So motivated by what we've been talking about, we kind of started to think about what it would be desirable properties of a treatment effect estimator. And we would like something that is robust to misspecification of the underlying time trend, robust to misspecification of the variance structure, and gives sensible results if the treatment effect is not constant, although given the caveat that we need to carefully define the treatment effect of interest, and as efficient as possible. So the approach we've taken, or I should say Fan has been taking, is based on the theory of structural nested mean models. This is an area developed extensively by Jamie Robbins and colleagues, originally to deal with complex questions in causal analysis, but turning out to be useful in this context as well. Basically, the structural nested mean model approach makes less restrictive assumptions than traditional regression models and exhibits some interesting so-called doubly robust properties. And I'll tell you in a moment exactly what I mean by those. So let's start with sort of a relatively simple approach and build it up. So first off, the structural nested mean model approach, you don't assume an entire probability distribution for your outcome. You only make assumptions about the first two moments. So in other words, I'm going to assume that the observation collected on individual K and cluster I at time J is a fairly simple function of a time effect, flexible time effect, and a treatment effect. And again, going back to assuming a immediate and constant treatment effect, though it'll be very easy to relax that assumption in this context. And then we also assume some variance structure for the observations. Sigma is an arbitrary covariance matrix, so it would be block. We assume it'd be block diagonal in the sense that clusters are assumed to be independent. So based on this, then, the structural nested mean model approach defines the efficient score and the efficient score will be set equal to 0 and then solved to get an estimate of the parameter of interest. And we can see that the efficient score basically involves the outcome data y, here expressed as a vector of the t cluster period means in cluster I, and the indicators for those T periods in cluster I, the 0, 1 indicators, treatment effect on or off. The time trend, which again, we're being very flexible here, so we assume that there's an arbitrary time trend, but that is constant across clusters, or at least across clusters within a strata. And then the weighting matrix here is essentially just the inverse of the covariance matrix for cluster I. So to form an estimator for delta, we set the efficient score equal to 0 and solve for delta. And so we get this generic estimator for the treatment effect delta hat, which is a function of the outcome y, the step wedge treatment indicator X, as well as the underlying time trend and the weighting matrix. The weighting matrix is basically a function of the variance components, or the variance structure. And so to solve this, we've got X's, we've got Y's, we need to plug in estimates for the variances, and we need to plug in an estimate for the time trend. But what makes this approach quite interesting is that the estimate of delta is consistent and asymptotically normal, even if the W's variance structure and time trend are incorrectly specified. And this is what's known as the doubly robust property. So if it turns out that this is consistent, asymptotically normal, no matter what W and beta I put in, maybe I should go for really simple assumptions about W and beta. So assume there's no time trend, okay? And assume that the data are independent. And if you make those assumptions, if you put it identity matrix in for W and you put 0 in for beta and solve this, you get this estimator, quite simple estimator for the treatment effect. And it turns out that this ends up being the exact same estimator that we derived back in, using a completely different approach, back in a 2020 paper in Biometrics. I can assure you that I had no clue at that point. I'm not sure I even still do have much of a clue, but I certainly at that point didn't have any clue about structural nested mean models. We came at this from a different approach, but it's quite interesting that estimator there basically can be derived from this same approach, and this is one thing that Fan has shown. So if you look at this estimator and work through it a little bit, what you see is that this is essentially based on the vertical comparisons of the intervention of the control conditions at each point in time. So this maybe gives you a hint as to why, in this case, it doesn't matter what time trend you assume, because all of the comparisons, all the estimates of the intervention effect are basically within a time interval. And so we estimate a delta here, we estimate a delta here, and then basically are combining them in a particular fashion to get an overall estimate of the intervention effect. Of course, we need not only to do inference, we need not only an estimate, but we need some sort of variation of that estimate, some standard error of that estimate. And so that can be derived, the variance of that estimate can be derived asymptotically using the structural nested mean model theory, or the approach we took in 2020 was by basically getting a design-based estimate of the variance of delta hat by reference to the permutation distribution. So again, going back to our simple case of only 3 clusters, 3 sequences here, there are 3 factorial or 6 possible ways those sequences could have been distributed amongst the clusters. I've listed those 6 possible ways here. You can derive basically a treatment effect estimate for each of these, and thereby compute the design-based variance of delta hat by getting the variance of delta across those different permutations. Now, clearly, as you get into more and more clusters and more sequences, this could become extremely computationally intensive. But what was interesting is in the 2020 paper, we showed that it's possible to get a fairly straightforward closed form expression for that variance, so you don't have to do all these permutations. So that gave us an alternative to an asymptotic approach that could get us a design-based sort of exact variance based on the design-based variation of delta. So basically then what we found was that this approach is robust to time trends and robust to variance structure misspecification, kind of inheriting that property from the structural nested mean models. With one caveat is we does assume that the variance structure, whatever it is the same across all clusters, and assuming a random treatment effect does violate that assumption, although we did find that the method performed quite well even when there was a random treatment effect. The biggest knock against this approach was it's extremely inefficient. So we basically have gained a lot of robustness, but sacrificed efficiency. So next step, so that's basically where we got to in 2020. What we're working on now is can we retain the robustness, but gain back some efficiency? So going back to our basically our estimator here, our generic structural nested mean model estimator, what if instead of putting independence sort of working correlation matrix in for W, what if we put in actually this wouldn't be W, this would be sigma, but what if we use basically an exchangeable correlation structure, assumed an exchangeable correlation structure? That's equivalent to putting in a random cluster effect in linear mixed models. Again, it doesn't need to be right, but similar to what you see with GEE, if your working correlation or assumed correlation structure is closer to reality, then you're going to get more efficient estimation. And so then that leads to this new estimator that depends now not only on the observed data, Y, and the covariate information, X, but also depends on rho. Now, again, we don't have to know rho perfectly, but the closer we get to rho in terms of putting it in here, the more efficient we would expect to be. So basically then the approach we've taken is that since rho is unknown, we estimate it based on the residuals. Notice that these residuals also involve an estimate of the time trend, although that again is usually pretty easy to do, putting in a very flexible time trend. The good thing is though still, none of this has to be correct for this to be consistent and asymptotically normal, but the closer you get to correct, the more efficient you'll be. So we expect now that this approach probably will be more efficient than the 2020 approach because this sort of exchangeable correlation is probably closer to truth than completely independent correlation structure. We can still get a closed form design-based variance, and as we'll see, this approach does improve efficiency. You can think of it as improving efficiency because it's not using not only those vertical comparisons to get an estimate of the treatment effect, but you can also think that it's using the within cluster comparisons to get an estimate of the treatment effect. Okay, and then we've also expanded this to allow us to incorporate the exposure time indicator model, where now instead of a single delta, we have a delta 1, delta 2, delta 3 at each exposure time. Basically, again, plugging things into the structural nested mean model estimator machinery. And think of this capital delta as just an X that captures the exposure time. It was just a notational sort of thing we had to develop. But again, keeping this this exchangeable working correlation matrix. Okay, so we're just beginning to do simulations. And so I only have one simulation slide, but just to give you a flavor of you know, what we're sort of seeing. So the simulation setting, basically I'm generating data with only a random cluster effect. Clearly we're going to have to do more simulations with different covariance structures. And I do allow, we have been allowing various sorts of exposure responses by this H. So is this H a curved or lagged or immediate treatment effect? I'm only going to show you the results for immediate treatment effect. And we have 12 clusters, 7 time periods, 20 individuals per cluster per time period, and an intercluster correlation of about 0.06. So let me just show you one slide here then. On the far right, so basically I have 4 different estimators I'm going to talk about. The TATE stands for total average treatment effect. In the case of an instantaneous and constant treatment effect, that's equivalent to what you would call the treatment effect. In other words, that's single delta, and that's the only one I'm going to show here. So if I fit a linear mixed model, basically the correct model with an immediate treatment effect with the correct covariance structure, it is unbiased as we would expect, and this is the standard error, and we would expect that since that's maximum likelihood, we can't beat that. What if we use the first structural nested mean model estimator I talked about? That's basically the used 2020 paper. We assume immediate treatment effect and we assume working independence. And we see that that is unbiased for the immediate treatment effect, but it is less efficient than the structural, than the linear mixed model. Now, what if we go to the exchangeable structural nested mean model? Basically, now that's got the right covariance structure, although we did have to estimate rho in this, but we basically see that we achieve virtually full efficiency compared to the linear mixed model, but we do retain the robustness properties of the structural nested mean model estimator. So that's kind of neat to see. And then what if we relax this assumption that the treatment effect is immediate and constant and instead basically fit the ETI model? Now, we didn't have to in this case because the treatment effect is immediate and constant, but it basically protects us against that assumption being violated. It's still unbiased. I guess it looks a little biased here, but that's just Monte Carlo variation. But more important is it's pretty inefficient relative to this or this. So we pay a pretty good price for that basically protection against the violations of the immediate constant treatment effect assumption. The only last remark I'll make is if you do all the same simulations, but under any of the other exposure time response curves, the curved or the lagged or the partially convex one, these all fail disastrously in that they're highly biased. This one remains unbiased, as you would expect, because these are all going to, anything that assumes immediate treatment is going to inherit that problem when that assumption is violated. Okay, so where are we going with this last slide? Obviously, we need to do more extensive simulations under alternative covariance structures, look at what happens with variable numbers of clusters, variable sample size per cluster. How important is it to get W right. In other words, get the assumed or working covariance structure right. And how important is it to make that dependent on potentially things like random treatment effects? We can do this issue of the asymptotic sandwich variance versus the permutation design-based standard errors, I think is really interesting. And what is the trade-off there? It is likely that a closed form for the permutation variance is not possible in general. It's possible in some of these special cases. So then how much is it better to rely on the sandwich variance or the permutation variance, especially as numbers of clusters get large? I suspect there'll be a trade-off there. And then, of course, extending this all to alternative links like log and logit, again, all possible within this structural nested mean model context. So that seems like a really good engine for that. So I will stop there and happy to address questions.
Thank you, Jim, for a terrific presentation. You've covered so much. I have a couple of pages of questions in front of me. We're never going to get through all of these, but we can at least get started. And there are more coming in all the time. I'm going to start with a couple of questions that came in late. So this most recent work is really exciting. The structural nested mean model seems a good way to deal with an intervention effect that varies over time, and seems to have less bias than models that are making an assumption about what that pattern looks like. But it's not very efficient, and so you're working on solutions, presumably, for that. When are we going to see this stuff in print? When are we going to see these papers? Because a lot of what you've presented is work in progress.
It is. So basically all this last part is stuff that Fan is really working and our group is working on now. You know, she's making good progress. I think she's really worked out the theory, and now we're trying to develop a really robust set of simulations to really understand the performance in various settings, the real performance, not just the asymptotic performance. The one thing I fear is that there's always going to be a pretty severe efficiency trade-off for assuming that ETI model that allows the treatment effect to vary over time versus building an assumption into the model that the treatment effect is constant. That's always going to end up being quite a bit more efficient. So I think it's going to be a trade-off of what you're willing to assume versus how flexible and how much protection you want. It's not going to be a simple choice.
Yeah, we're often faced with that kind of situation.
Yeah.
Another question about all this new work. You didn't mention what sort of software you're using to run the simulations or to analyze the data. Are the papers going to include code for something like Stata or SAS or R?
Well, basically we're doing it all in R, and we basically in our papers we're always trying to put in appropriate R code to do simulations or whatever. So as a supplemental material, so we'll certainly include that material.
Yeah, I'll put a plug in for including at least analysis code for the analytic models in Stata or SAS. Because a lot of people are using those still for data analysis. They may not be doing simulations like you are, but they may want to apply your models.
So the difficulty there, I guess, is, well, of course, not super familiar with Stata and SAS, but developing new estimators like a structural nested mean model estimator can you actually program those things up in state and SAS very straightforwardly like you can in R?
Fair question. Fair question.
Okay.
So maybe you publish the papers and you do it in an R, and then SAS grabs it and
That'd be
develops
great.
an estimator. So that, I mean, we've seen that happen many times. So I'm going to go back to some sort of fundamental things after asking those sort of end of the talk questions. Your slide very early, might have been the third slide, where you talked about a common analysis approach, had both a fixed effect for intervention and a random effect for intervention. And in a parallel group or cluster, random effect for intervention. So why is the situation different in a step wedge? Is there, how else would you describe that random effect for intervention to help us understand what it is?
So, I think in the parallel design, I don't think it's separately estimable. But in step wedge, because you've got the crossover within each cluster, you can get an estimate of it, and I think the point is not so much to estimate a intervention effect for each cluster as to account for the additional variation that might be induced by differential effects. And you can certainly imagine if it's something like a training intervention in healthcare providers, that it might take better in one setting than another, or in one clinic than another. So I think it's trying to account for those sorts of additional variations, additional uncertainty.
Is it essentially a random effect that's an interaction between intervention and cluster?
Yes, yes,
Yeah.
that's
Okay.
exactly the way to think about it.
All right. That helped me, and I hope will help others. At one point, you said there was no penalty for overfitting variance components. Aren't you using up degrees of freedom? Isn't that a sort of penalty?
Well, the degrees of freedom are only the fixed effects, right? Based on fixed effects. But um, you might expect that you would perhaps lose efficiency by fitting too many variance components, but what tends to happen is the ones that aren't necessary get fit close to the boundary anyway, and so have very little effect. So what we've found in simulations is that you remove the issue of potentially wrong variance structure, wrong standard errors, but you don't end up having less efficient estimators. I don't know if there's a theorem about that or not, but that seems to be what we've observed.
Later on in the presentation, you warned against using the immediate and constant treatment effect model, what you called the IT model.
Yeah.
But isn't that exactly the model you proposed in Hussey and Hughes
Oh, absolutely.
in 2007?
That is
Yeah.
exactly it.
And I can tell you that when I look at grant applications that come to NIH, that's what everybody proposes for
that's
their
what
analysis.
everybody uses, right?
Yeah, that is the standard
and
thing.
I
So
think,
how do we communicate with the community that things have evolved?
well, I think through doing well, so the paper is still under review at Statistics in Medicine.
Yeah.
We're quite hopeful. So that will be out soon. I think the issue here is the fact that the standard model, as I said, does not fail gracefully. You know, if it gave some sort of reasonable estimate when the assumption was violated, we wouldn't be too concerned. It's the fact that it can give these very unreasonable estimates when the assumptions are violated that I personally find so worrisome. So I think we have to collectively, as we work with researchers and give presentations, to get the word out that they need to think about that assumption very hard, not just use the standard model because that's the one everybody uses.
Right. Well, your colleague Patrick Haggerty, who works with us on a couple of initiatives, and I and others have been trying to push that point, but boy, everybody starts with Hussey and Hughes. That's where everybody lands to begin. So the result you showed, where that IT effect estimator gives counterintuitive results was certainly surprising. It was surprising to you. It was surprising to us. Yes, that figure. That's my favorite figure in the presentation.
Exactly.
Is this the result of is this a result because the first time period or the first couple of time periods is particularly influential compared to the others? Is there some other explanation?
No, you're on exactly the right track. So, and I really want to thank, I don't know if he's online here, but Andrew Forbes, colleague in Monash University in Australia, because I sent a preprint of this paper to him, and he actually provided a paper that led to a really Okay, so what's happening? So this is our cluster randomized trial. We have 1-time unit, 2-time units, delta 3-time units. The estimate of delta that you get from the IT model is basically a weighted sum of the 1-time unit, 2-time unit, 3-time unit estimates of delta. The issue is that although the weights sum to 1, as you expect weights ought to do, but they can be greater than 1 or negative. And so this is really bizarre. I mean, the fact that these weights can be negative. And what happens in particular in the step wedge design, looking at this, is that the weights here are much greater than 1, but they get multiplied by 0. And the weights at the end are negative, and they get multiplied by this value. And so the overall estimate becomes this negative value. And this sort of thing can happen, this phenomenon can happen when you have multiple estimators of what is purportedly the same quantity. In other words, delta 1, delta 2, delta 3 are all supposed to be estimating the same thing under the IT model, but you have multiple estimates of the same quantity that have different precisions. So delta 1 is based on more information than delta 3, but are nonetheless correlated. And these delta 1, delta 2, delta 3 are correlated because there's correlation within the clusters. So you have multiple estimates of the same underlying parameter that have varying precision but are correlated, and you can get this sort of phenomenon. And so that's sort of what's going on here.
Thanks very much for that explanation. Is the alternative treatment effect estimator that you offered towards the end of your talk a solution to this problem that we've just been talking about, so that it allows you to more accurately estimate the effect of the intervention rather than forcing?
So it is. So basically, the so-called exposure time indicator model is unbiased under any basically scenario of exposure time response. It's just the efficiency. So you're gaining the unbiasedness. It's going to fail gracefully if you assume that I'm going to throw away the first 2 exposure times and use only 3, 4, 5, 6 and average them, and they're really not constant. Well, you'll still get a reasonable average. You won't get something that's sort of the other direction, but you're losing the efficiency.
Okay. There's so many questions to choose from. What impact does variable cluster or group size have with that structural nested mean model? We know that it's important with mixed models, but what about the structural nested mean?
Great question, and for sure, it's going to have an impact. We can build that in. Again, that's the nice thing about this approach is the work Fawn has done, which I've sort of almost presented simply a cartoon of here. It's much deeper what she's actually done. Does allow variable cluster sizes. How that works in simulations we'll have to work out, but the theory works. And I think the biggest issue there might be that I think that we won't be able to get
back to Dr. Moyer. Thank you very much for your presentation.
Thank you.
Thank you, Dr. Murray, Dr. Hughes, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. You will receive an email with a link to the recording when it is available. Thank you and have a great rest of your day.